Congratulations, you are almost at the end of all of the programming assignments. Hopefully you are ready to start in on the 10th and final weekly programming assignment, assignment 10. We'll talk a little bit about assignment 10 in a moment. Next Tuesday, you will be, or next Monday night, you will be submitting assignment 10, and Tuesday morning, you'll be ready to move on to your final project. I will set aside about 20 minutes at the beginning of class on Tuesday to talk about what the final project is, expectations, projects that students have done in previous years to give you a sense of sort of what's possible and what's out there. Sound good? Okay. Assignment 10, we are going to kind of switch gears yet again. And up until now, you have been working with our quote-unquote robot that's made up of 3 links and 2 joints and 2 or 3 sensors and 2 motors. It's about as simple a robot as we could possibly make in the PyBullet physics engine. In preparation for your final project, we are now going to not add any new functionality. You're just going to complicate the mechanical structure of your robot. So you're going to be expanding your 3-link robot into a 9-link robot that looks like this, which we have seen a few times before. Not like that. There we go. 9 links, 8 joints, 4 touch sensors in the 4 lower parts of each of the 4 legs. 4 touch sensors. We've got 8 joints, so you'll have 8 motor neurons, 8 motors. You're going to connect each of the 4 sensor neurons to each of the 8 motor neurons, which will give us 4 times 8, 32 synapses. If you want to add in hidden neurons, that's perfectly fine. Okay. So that's the quadruped. It's quite a few steps. Again, it's quite a few steps. Not that many steps. 60 steps to implement the quadruped. What I suggest as you go along, and this is optional, is to create an engineering drawing. For those of you that have ever taken an engineering class, you've probably made a drawing like this before. We've got the top view, the side view, and the back view of your quadruped. And as you build it up, you're going to strip it down to 3 links, because you already have 3 links, and then gradually build it up to 9 links and 8 joints. As you add each joint and each link, I would jot down on your engineering drawing here the coordinates for each link and each joint, so you re-familiarize yourself from the combination of absolute and relative coordinates that are used in PyBullet. Yeah. You could, of course, obviously add everything in at once, cross your fingers and run it, but hopefully by now you'll get a sense that that's often not a good way to go. We'll do this 1 link, 1 joint, 1 sensor neuron, 1 motor neuron at a time. So it's a lot of fiddly steps, but as long as you take things 1 small step at a time, assignment 10 should be straightforward. And at the end, you will have a parallel hill climber that's evolving at least 32 synaptic weights to cause the quadruped to move in PyBullet. Pretty straightforward. Yep. Any questions about that? All good? Okay. So back to our theme on open challenges in the field. Last time we finished looking at modularity and allowing evolution to build in modularity if needed. And we started in last time by introducing NEAT, which is a solution to a problem, and that problem is the competing conventions problem, where if we're evolving populations of neural networks, we would like to do a couple of things. One of those things is to allow the evolutionary process not just to optimize the weights of the synapses in a neural network with a fixed topology, but we want to broaden the evolutionary algorithm to be able to tinker with the topology or the architecture of the network itself. That's challenging already, but if you do allow your evolutionary algorithm to do that, you're going to end up with a population of neural networks, some of which are better at different subfunctions that make up whatever problem you're trying to get the neural networks to solve, and they're going to have different topologies, different architectures. Can we introduce crossover, which cuts networks in half and then tries to glue the parts back together to produce a child that sometimes, by chance, is a combination of the best of both worlds. Good parts of different parent networks in the population that have different architectures. A very, very difficult thing to get right. This is what NEAT was designed to do. The way NEAT solves this problem, and I gave you the intuition for this last time, is if we have two networks down here and we want to figure out how to cut them up and how to align them so that we copy only one unique subfunction or one piece into each child. We're going to use the intuition that we can identify in each pair of networks particular parts that are likely to compute similar subfunctions because they are evolutionarily derived from a common ancestral network in which there was only one copy of that piece. And I'll show you some examples of that right now. Okay, so we talked about the genetic encoding for NEAT last time. Each genotype is a pair of lists. One list denotes all the neurons and all their properties. The second list denotes all the synapses and all their properties. And you'll notice that the synapses have associated with them this variable here called innovation, which is short for innovation number. So every time a mutation adds a neuron or a synapse to the first or the second list, respectively, we're going to keep a global counter. We're going to take the current value of that global counter and assign it as the innovation number for that new thing that we're adding to the current genome. So in this example here, we have this particular network. It has 1, 2, 3, 4, 5 synapses in them. These synapses already have these innovation numbers assigned to them. We're assuming at this moment in time, a mutation hits this network and adds this synapse here, the synapse that connects neuron 3 to neuron 4. We pull off the current value from this global counter, which in this example happens to be 7, and we assign that number to that synapse. We increment the counter to 8, and the next time a mutation occurs anywhere in the population, that new neuron or synapse gets that innovation value of 8. So in this example here, assume, I guess in this cartoon it looks like it's the same network. Assume this is a different network in the population. It also gets hit with the mutation. In this case, the mutation is going to add a neuron that sits between neuron 3 and 5. We're only showing in this cartoon the list of synapses. We're not showing the list of neurons. We've added a neuron, and then we're going to add 2 additional synapses to wire in this new neuron to the network, one that connects neuron 3 to the new 6, and another one that connects the new 6 to the 5. So we're adding 2 new synapses, which get values of 8 and 9 from the global counter. So far, so good? Okay. This value, this innovation number, is going to allow us, when we try and perform crossover, to line up parts of each of the parent networks that we assume are going to have similar function. So in this example here, let's imagine we have these 2 parent networks here. And here is, again, just the list of synapses for each of these 2 parents. They share some genetic heritage. Some parts are derived from a common ancestor. Some parts aren't. Which is which? If we look at the genomes of these 2 parents, what parts do they share in common? And how do you know? You'll notice that if we look at synapse 1 in parent 1, this synapse 1 connects neuron 1 to neuron 4. That's this one here. It has an innovation number of 1. There is another synapse in this parent which connects neuron 1 to 6. It has the same innovation number. What that means is because they have the same number, they must have derived from an ancestral parent network that they shared in common. And inside the genome of that common ancestor, there was only one copy of synapse 1. When that common ancestor started to produce offspring, and those offspring produced offspring, and those offspring produced offspring, they inherited this particular synapse that had this innovation number. So when we copy a network, we copy those innovation numbers and they flow down through the descendants. Yeah? So they both share synapse 1. Synapse 2 appears in both places as well. We get to synapse 3, and we notice the innovation number 3 here, synapse 3, only appears in parent 2. It does not exist in parent 1. So somewhere in the ancestral line going from the common ancestor down to parent 1, somewhere in that line there was a mutation that added in a new synapse, synapse 3 here, that did not appear in parent 1. Or alternatively, the two branches coming down from the common ancestor, they both had synapse 3, and somewhere in the ancestry of parent 1, synapse 3 was deleted by a mutation event. Mutations can add or remove synapses, add and remove neurons. So far, so good? Okay. So when we go to cross parents, they are networks, so it's hard to see how to line them up. So on purpose, in NEAT, the genetic encoding of these networks is a list, is a string. We're going to take those two strings and treat them like actual DNA, where we're going to try and line up parts of the DNA between these two parents that we assume have similar function based on the fact that they were derived from a common ancestor. So we start with the first synapse in parent 1. It has an innovation number of 1. We go looking in parent 1 to see if there is a corresponding synapse that also has an innovation number of 1. There is, so we line it up here. Same thing here, we take synapse 2, place it in the list here, go looking for synapse 2 in parent 2, we find it down here, we move on, and in this case, synapse 3 exists in parent 2, does not exist in parent 1, so we just leave that slot blank, we line up 4 and 4, we get to 5, 5 only exists in parent 1, not in parent 2, so we leave the slot in parent 2 blank, line up 6, there's no corresponding 7 or 8 in parent 1, and we've now lined up these genomes. Now we can walk across this aligned list, and as we go, every time we're going to flip a coin, heads, we're going to copy the synapse from parent 1 into the offspring, and tails, we're going to copy in the synapse from parent 2. If we get to a point in which there is only one copy of that synapse in one of the parents, we can again flip a coin and either include it or include nothing at that point. In this case, they included both 3 and 5 into the child, which gives us now a list of synapses describing this new child. We do exactly the same thing with the list of neurons, just isn't shown in this cartoon. And if we then reconstruct the network that corresponds to this genotype, we take this genotype and turn it into this phenotype, we get a child that looks similar to parent 1 and parent 2. It has similar structure, but we have no guarantee that child 2 will behave similarly to parent 1. And when I talk about behavior for the neural network, it means that if the child receives the similar sensory input to the two parents, it will tend on average to produce similar output. The chance that a child network will behave similarly to the two parents has been increased by the NEAT algorithm, by trying our best to approximate or estimate redundancies in the two parents. We don't need both synapse 1. We just need one copy. Make sense? Okay. It's a relatively old paper at this point. It's 20 years old. This is a very, very common algorithm used in lots of different branches of AI, not just evolutionary robotics. Okay. Okay, that's the NEAT algorithm. You can go and have a look at the original paper. If you go and Google neural networks through augmenting topologies, you'll see this is used in lots and lots of different branches of AI. Any questions about NEAT before we push on? All good? Okay, I want to talk about the second part of this lecture now. We're going to start in the second part, which is introducing an algorithm that builds on top of NEAT called HyperNEAT. And HyperNEAT was meant to solve a different problem. And I'm not going to talk about that problem yet. I want to talk about HyperNEAT first, and then we'll see how HyperNEAT solves this problem. Okay. HyperNEAT is going to evolve neural networks, very much like we've seen many times in this course. HyperNEAT evolves particular kinds of neural networks, which we haven't seen yet. These are known as compositional pattern producing networks, or CPPNs. And HyperNEAT evolves populations of CPPNs using NEAT. We're going to evolve a population of these CPPNs. Mutations can add or remove neurons and synapses from CPPNs. NEAT is also going to cut parent CPPNs and try and line them up and combine similar parts together, as we just saw in NEAT. We're going to focus, so most of HyperNEAT should look familiar. We're evolving populations of neural networks. The parts that's new in HyperNEAT for us are these CPPN networks. So we're going to talk a little bit about CPPNs now. CPPNs are neural networks. Most of them most of their features are going to look similar to you or familiar to you already. They are collections of neurons, which you see here, and we've got arrows which are connecting up these neurons. You'll notice there's a little figure inside each neuron. We'll talk about that in a moment. So they're neural networks. They have an input layer. They have some hidden neurons in between, synapses that connect hidden neurons, input neurons to hidden neurons and connect hidden neurons to output values. The major difference between CPPNs and all the networks we've seen so far is how their input neurons behave. In a traditional neural network that's trying to recognize cats in a YouTube video, the input to the neural network are colored pixels from an image or a video stream, and the output is a classification. In this course, we've seen many neural networks now, and you've now built several neural networks where the input values are capturing values from sensors, transforming them into motor outputs. In a CPPN, the values arriving at the input neurons are coordinate values. How does this work? I'm just going to skip ahead. I'll come back for a moment. In essence, what CPPNs do, or HyperNEAT evolved CPPNs to do, is to paint regular patterns inside a cube of arbitrary dimension. So if we go beyond dimension 3, we're into hypercubes, and we'll see how CPPNs paint patterns into hypercubes. But the hypercubes is where the hyper in HyperNEAT comes from. Okay. So in this little cartoon example here, this little picture of this insect, we're going to deal with the hypercube of dimension 2, otherwise known as a square. We're going to take this square, we're going to take one CPPN out of the population of CPPNs that HyperNEAT is evolving, and we're going to then visit a regular set of x and y coordinates inside this square. So imagine we drop a lattice onto this square that has regular coordinate values. We can drop a lattice of higher resolution, meaning we're taking relatively small steps in this lattice, or we can drop a lattice of low resolution, and we're taking relatively large steps. Let's start at the first point in this lattice. Let's assume it's x equals 0, y equals 0. We take those two values, 0, 0, and we feed them into this neural network. And as we've seen many, many times before, we propagate those values through the network. And in this simple example here, let's imagine at the output, we have just one value, which indicates what color to paint this pixel. I know this cartoon is in color here. Let's just imagine it's in black and white for a moment. We can treat the single value arriving at the output as how dark to paint that pixel at 0, 0. So far, so good. We go to the next point in the lattice. Let's assume that next point is x equals 0.1, y equals 0. We plug 0.1 and 0 into the same network. We haven't changed the network yet. Flow through, and we get a different value, which indicates what color or what amount of gray to paint that pixel. We go on to 0.2 and 0, and so on and so forth. And this neural network ends up painting some image inside this square. So far, so good? Okay. We'll look at the details we'll actually look at an example on the board in a moment. The amazing thing about Cppns, and we'll see why in a moment, is that if you create a random Cppn, you create a whole bunch of neurons, you connect them up at random with synapses, you assign those synapses random weights, you have a random neural network, as random as you can make it, it will not paint a random picture. You're not going to get a random smear of black and white pixels. You end up getting something that has regularity in the image. There are various kinds of regularity that you end up getting out of Cppns, and that's what this cartoon is meant to represent. One thing you tend to get is repetition. So if we look along the y-axis here, as we imagine this neural network painting grayscale values inside the square, it might end up repeating the broad pattern it's painting along the y-axis, corresponding to the different segments you see in the little cartoon bug here. Another type of regularity you tend to see in Cppns is symmetry. So in this case, it's also painting something that is bilaterally symmetric on the x-axis. We've spent a fair bit of time talking about the biomechanics of motion at this point. Bilateral symmetry, or symmetry in general, is a pretty good thing in animals and in robots, anything that needs to move. Cppns can combine and recombine different kinds of regularity. So here we've got repetition on the vertical axis, symmetry on the horizontal axis, and it can also add additional details that don't have any repetition or any regularity whatsoever, represented by the little heart here, the one instance of some detail that's painted at some particular place inside this image. If we step back for a moment and think about hyperneat evolving populations of Cppns, given the way Cppns work, they tend to focus evolution within one part of the space of all possible images that could be painted. Remember our discussion about the fitness landscape, where we had a landscape that existed in high dimensions, and all the horizontal dimensions corresponded to parts of the genotype. They corresponded to genes. In hyperneat, you can imagine, again, a very high-dimensional space. We got a whole bunch of horizontal dimensions corresponding to all these synapses inside a Cppn, and the height is the fitness of an image. I don't know how we compute the fitness of an image for a moment. We're going to just disregard the vertical axis for a moment. You think about that vertical space, every point inside, if you think about that horizontal landscape in the fitness landscape, every horizontal position corresponds to a different Cppn, and it corresponds to a different picture. So if you think about the space of all possible pictures you could paint within a 200 by 200 square, let's imagine, the vast, vast, vast majority of all of those images are going to be white noise. They're going to look like static you get on a old school television, right? Just random black and white pictures. Things like this, pictures that have regularity, repetition, contiguity, meaning there's just one whole blob. It's a vanishingly small subset of all possible images. What hyperneat tends to do is jump in this smaller space. It's called a manifold. We're not going to go into the manifolds in this class, but manifold is just going to be our term to correspond to this very small subset of images that we're potentially interested in. Not the vast majority of things that are just white noise. Images with regularity, repetition, symmetry, contiguity. And then within that small space, we might be looking for a particular image that's particularly of interest to us. We're going to have a fitness associated with images and go looking for them. So far, so good? So Cppn is restricting or biasing where the evolutionary algorithm moves in this very vast landscape of all possible pictures. Okay. How does it do that? We're going to dive into a little bit more detail of the CPPN. And I'm going to use my, this is going to be my phenotype. This is going to be my X and Y. And then over here, I'm going to create a genotype. So let's create a very simple CPPN. So we need our two input neurons, X and Y. And we're going to have one output neuron B, which is the amount, actually let's call it G, the amount of gray we're going to paint into a given position. So far, so good? Okay. Let's add a single synapse, and let's give it a weight of 1.0. We now go to x equals 0, y equals 0. We plug 0, 0 in here, and without me even telling you what activation function we're hiding in G here, what value are we going to get at the output? We plugged 0, 0 into the input. 0, right? Okay, so 0 gray in this particular pixel. Let's assume that inside our G neuron, I'm going to make this a little bigger, we're going to imagine a particular activation function, and we're going to draw that activation function as a graph inside the neuron. We're going to have a little x in here and a little y in here. These are different x's and y's from over here. The x value here is going to be the raw sum that arrives inside the neuron. And the y value is going to be the transformed value that this neuron sends out. So if we use a linear activation function, y equals x, that means whatever raw sum arrives in here, we send the exact same value out, right? We just had 0 times 1 equals 0. 0 arrived here. X equals 0 gets transformed into y equals 0, which came out as the amount of G. G equals 0. We have a white pixel here. So far, so good? Okay. Next pixel, x equals 0.1, y equals 0. How much G comes out? Point 0.1. So we've got a little bit of gray in here. We go to the next one, x equals 0.2, y equals 0. How much G do we get down here? 0.2, a little bit more. And if we keep going, we're going to get an increasingly dark gradient from x equals 0 to x equals 1. Let's do the next row. X equals 0, y equals 0.1. How much gray in here? 0 and 0.1. X equals 0, y equals 0.1, 0. As we move along this row, what happens? How does this row get painted? Same as the first row, right? It gets increasingly dark. And if we continue this for all the rows, what we're going to get is a gradient of darkness moving from left to right. Yeah? Okay. One CPPN, one picture. Where's my eraser? There it is. Okay, we're going to do exactly the same thing, but we're going to create a different CPPN now. We're going to erase the synapse that connects X to G, and we're going to add a synapse that connects Y to G with the same weight, 1.0. What pattern is this CPPN going to paint inside our square? Vertical gradient, right? It's going to get darker as Y becomes greater. How about this? What picture does this paint? Exactly, right? Up and to the right. Things are going to get darker as we move up and to the right. Okay, let's do one more. One other distinguishing feature about CPPNs is not just how we feed values to the input layer, but the innards of the neurons themselves. In a CPPN, we can evolve not just the synaptic weights and the neural architecture, how many neurons and which neurons are connected to which other neurons with synapses. We can also evolve the activation function that exists inside of each neuron. And that's what our cartoon on the left of the slide is showing us. We can see we have 1, 2, 3, 4, 5, 6 hidden neurons. And each of those hidden neurons has a different activation function inside. Okay, we're going to leave everything as it was before. We've got our X, our Y. We have a linear activation function inside the output neuron, which is going to tell us how much gray or how dark to paint the pixel. And we're going to add a Gaussian activation function, meaning that the more positive or the more negative the raw weight, the weighted sum that arrives at this neuron, the closer to 0 this neuron is going to output. The closer the raw sum is, the weighted sum is to 0, the more positive a value this neuron is going to output. Okay, this one's a little trickier to think about. Let's do a couple of pixels to build up our intuition. We've got 1, 2, 3 synapses. Just to make our lives easier, let's assume the weights are 1. 0, 0 arrives here. What arrives down here? We fit in the coordinates 0, 0. How much gray are we going to paint onto that pixel? 1? Okay. I actually should have specified, let's assume the height here of this Gaussian is 1, right? 0 times 1 is 0. 0 times 1 is 0. 0 arrives in here. The neuron spits out a value of 1. 1 arrives in here as the weighted sum, and it spits out a value of 1, and this is painted maximally dark. What picture does this CPPN paint?
Is it darkest? Oh, never mind.
Let's do 1, 1 up here. Let's paint this pixel. We feed in 1, 1. 1 times 1 plus 1 times 1 is 2. Let's assume it's way out here. This neuron outputs a value of 0. 0 arrives down here. 0 arrives out here. This pixel is painted white.
Is it a diagonal gradient, or is it a little more complicated than that?
Let's see. Let's do another one. 1, what is that? X equals 0, y equals 1. 0, 1. 1 times 1 is 1. It's a little difficult to see from my little cartoon here. It's 0.5 in here. Okay. I'll leave this as homework. I think it is a little more complicated than just a single gradient. Okay. If we keep going, if we keep adding neurons and synapses, you'll notice that at every neuron, we're computing a function. And these functions tend to be composed together, right? We're computing a function of a function of a function, which is the compositional part of compositional pattern-producing networks. You can see how CPPNs are networks. They're made up of neurons and synapses. You can see how they produce patterns. They produce patterns by composing coordinate transformations. We're feeding in coordinate values, and we're getting some transformation of those coordinate values. In the first example we saw when we connected X and Y directly to the output neuron, there was no composition. It was just one coordinate transformation. Now, in this cartoon here, we're doing 3 coordinate transformations, where this is a transformation of this is a transformation of this, and this is a transformation of these coordinates. We're composing coordinate transforms, which is sort of swirling everything around and ends up producing a pretty picture. Yeah? Okay. Again, it's kind of fun with pen and paper or on your computer is to just write down a random CPPN and you'll notice that it tends not to produce random pictures. It composes regularities together to produce gradients, repeating patterns, symmetry, and so on. Okay. Why we would use a CPPN to paint pictures in 2 dimensions, I don't know. There used to be a website, I don't think it's active anymore, you can check it out, called PicBreeder. PicBreeder was kind of a citizen science project. You could go to PicBreeder and you could choose which images you thought were prettier than other images. And then HyperNeat would delete all the images, would delete all the CPPNs that painted pictures that you didn't like. And it makes randomly modified copies of the CPPNs that painted pictures that you liked and repeated this process. You were the fitness function. Okay. I don't know if PicBreeder is active anymore. If you go to YouTube and you YouTube PicBreeder, you should be able to see a video of it in action. Okay. HyperNeat, like Neat, is a pretty common tool used in various branches of AI, including evolutionary robotics, and we'll see an evolutionary robotics application in a moment. Obviously, in evolutionary robotics and other branches of AI, we're not interested in painting regular patterns onto a canvas. We're interested, depending on our application, on painting patterns onto different things, and we're going to see that in a moment. How do we get HyperNeat to paint patterns onto different things? One of the nice things about CPPNs, or HyperNeat, is it's relatively easy to alter it so that it paints patterns at least onto things of different dimension. I mentioned hypercubes before. We just saw a CPPN that paints patterns onto a hypercube of dimension 2. How do we get HyperNeat to paint patterns inside a cube, a hypercube of dimension 3? How do we have to change HyperNeat so that now it paints patterns inside a cube instead of a square?
Would you just add a third input neuron, so like the coordinate?
Absolutely, right? And again, with pen and paper, you can try this. This will now paint regular patterns inside a cube. We're actually going to see in a moment an application where we're going to paint patterns inside a hypercube of dimension 6. And we'll see why in a moment. HyperNeat is fun because, as I mentioned, it tends to bias evolutionary search towards regular patterns. Any musicians here? Obviously, we want to try and paint notes in a regular pattern. If we play random notes, we usually don't get something that's very subjectively satisfying. How could you alter HyperNeat to compose music?
Give it some memory.
You could give it some memory. Okay, maybe it needs to remember what it painted in the past. What change do we need to make just so, I mean, obviously here it's painting pictures. Now we need it to write music.
Like a one-dimensional input for time.
Absolutely. So we're going to have time on the horizontal axis. So we're going to replace x with t. What goes on the vertical axis? We're going to move along and it's going to write music over time.
Notes or chords.
Notes, right? Or frequency if we want to be scientific about it, right? So we could query a bunch of candidate frequencies, lower tone, higher tone, lower tone, higher tone. And at each point, we could feed that in. I'm going to just write this as hertz. I'm not musically inclined myself. I think better in terms of frequencies and hertz, but you get the idea. We're going to feed in at a particular time a candidate frequency. And we could look at the output value, and we could simply scale it to a binary value or clamp it to a binary value 0 or 1, which indicates whether to place a note at that position or not. Again, I can't read or write sheet music, but I think you get the idea, right? Okay, so we can alter HyperNeat to paint images, write music. How about generate an animation? What change would you need to make so that each CPPN produces a moving picture, an animation?
An X and a Y for the picture and then a T for the time.
Absolutely. We'd have 3 input neurons, X, Y, and T, right? So with relatively little changes, we can change the dimensionality and what pattern is being produced. And in terms of pictures, music, and animations, we don't want to search all possible musical scores that are random collections of notes. We don't want to search the space of all possible animations, which is just changing white noise. We want to restrict evolutionary search to regular patterns. You can probably see how this is a relatively powerful idea, and with relatively few changes, you can apply it to lots of different domains where regularity is useful. But what particular regularity you want, that's up to evolution. Okay. So back to evolutionary robotics. In evolutionary robotics, we're going to, in this particular experiment here, the roboticists used HyperNeat to paint synaptic weights onto a neural network that controls a robot. Okay. At first glance, this should seem pretty strange. We're going to evolve populations of Cppns, which are themselves networks. Each Cppn is going to produce another network, and that network is going to control the robot. Why? Why would we add in this seemingly unneeded wrinkle of complexity? Why not just evolve populations of neural networks for robots directly, like you're doing in your final project? What might HyperNeat buy us here?
Like having different parts of the neural network do specific tasks as opposed to having it be like super integrated.
Possibly, right? So we just finished talking about modularity. It's possible that HyperNeat will produce more modular solutions than if we just evolve synaptic weights directly and we get this whole mixed up ball of spaghetti. It's a possibility.
You have more regular movement?
You have more regular movement because the pattern of synaptic weights is also regular. Question mark, right? It's not immediately obvious that that's going to be true. And that was the hypothesis that the authors here were actually investigating. As we learned from our discussion of locomotion, obviously you don't want a legged animal or a legged robot with all the legs doing their own random thing. You'd like coordinated motion. Either legs are moving together or legs are moving in perfect antiphase or some other combination of regular motion. Does a robot or an animal controlled by a neural network that has regularity, repeated patterns, gradients of synaptic weights over the neural network tend to bias evolution towards regular gaits? That was the question they wanted to ask in this experiment. Okay, so first, before we can answer that question, how do we get Cppn to paint patterns? How to paint, in this case, not grayscale or musical notes. We're going to paint W, the weight of each synapse, onto each synapse in this network. As you can see in this picture, the first thing they did was to embed the neural network into a three-dimensional space. Up until now, we've been talking about neural networks, and obviously we've seen pictures of neural networks, but the neural networks themselves didn't really have any geometry. They only had topology, which neuron was wired up to which other one. There was no sense that two neurons were farther away from each other or closer to one another. Now, in this neural network, which is the one that's going to control the robot, there is some geometry, and that geometry is going to matter, as we'll see in a moment. Here's our three sets of synapses. We have all the input neurons trapped in the input plane here, trapped in a 2D plane. We have all of the hidden neurons trapped in a different 2D plane, and we have the 1, 2, 3 times 1, 2, 3, 4 output neurons trapped in another 2D plane. Let's see if I have a picture of this. There's a picture of this network. So we're going to, again, be working with the quadruped. In this case, each of the four legs has 3 mechanical degrees of freedom, 3 motors. 1 in the knee, as we've seen before, and 2 in the hip. One that allows the leg to sweep inward and outward from the body, and a second one at the hip
that allows the leg to swing forward and backward. Yeah? Three motors per leg. We have 4 legs. We have a total of 12 motors, 12 motor neurons. 1, 2, 3, 1, 2, 3, 4. 3 times 4 is 12 motor neurons. Okay, so that's our motor neurons. Let's have a look at our sensor neurons here. On each row here, we have all of the sensor neurons dedicated to that leg. You'll notice here we have cur, which is short for current, and output layer is next. Current represents the current angle of that motor. So these 12 sensor neurons here, these are sensor neurons receiving proprioceptive sensation. The 12 angles of the 12 motors at the current moment in time. The angle of the forward and backward hip, inward and outward hip, and the angle of the knee. We have an additional 4 touch sensors, 1 in each of the 4 lower legs. And then they threw in a collection of additional neurons here. They have 3 more that give back orientation information. Pitch, how much the robot is pitched forward and back. Roll, how much the robot is rolled around its long axis. And yaw as well. So we've got 3 additional numbers giving the orientation of the robot's body. And then another neuron that outputs a sine wave. What is this neuron? We've seen this before. In you, it's not a single neuron. It's actually a cluster of neurons that produces a sinusoidal pattern as well. The central pattern generator, right? We know from us and from headless chickens and from some previous robotics experiments that generally speaking, it's useful to send a regular sinusoidal pattern into the network. If evolution finds that it's not useful, then it'll tune the weights and it'll basically silence that neuron. We're offering it up as potential useful raw material. Okay. They didn't draw the synapses here, but we could imagine there's a synapse going from each of the 20 sensor neurons to each of the 20 hidden neurons, and then another synapse going from each of the 20 hidden neurons to each of the 12 output neurons. To make our lives easier this morning, we won't assume any recurrent or self connections inside the hidden layer. How would you get a Cppn to paint weights onto all of those synapses? How would you construct your Cppn? First of all, what dimensionality would you use? How many input neurons do we want to have? What seems like the first obvious choice? Five? Okay. What are the 5?
I was thinking of for each input neuron.
Remember that in a Cppn, yeah, exactly. This is a little tricky. We're painting weights onto this neural network. We're painting weights onto the synapses of this neural network. The neural network itself is embedded in 3-dimensional space. Each of the neurons has a coordinate in 3-dimensional space. Makes sense. We should start with 3, right? If you imagine each synapse flowing from, let's say, this sensor neuron to this hidden neuron, you imagine this arrow. If we take the midpoint of that arrow, that midpoint also has a 3D coordinate. If we consider another synapse that connects this neuron to this neuron, it also has a midpoint somewhere around here that also has a 3D coordinate. So why don't we just feed in the x, y, and z coordinate of the midpoint of every synapse. And we wire this up somehow. And if we plug in the 3D coordinate of any given synapse inside this network, it's going to give us back a weight for that synapse. We now have a Cppn that can paint weights onto synapses inside a neural network that's embedded in 3D space. Everybody see that? Okay. Given all of that lead up, you can guess that this isn't actually going to work. What's wrong with this approach?
Some midpoints are going to overlap.
Absolutely, right? So if we were to actually draw these synapses, there's going to be a lot of them that share the same midpoint. What's the repercussion of that fact?
Two weights that are calculated the exact same way.
Absolutely, right? So any synapses that share a midpoint, by definition, they're going to get exactly the same weight. So it's a bit of a drawback to the, we're constraining the evolutionary algorithm. It cannot, there is no CPPN in the space of all possible CPPNs that would produce different weights for those sets of synapses that share a midpoint. It may be, because evolution is smarter than we are, that maybe it doesn't matter. Despite that limitation, it's still able to evolve sets of synaptic weights that control the robot and allow it to do whatever we want the robot to do. But let's roll back that assumption. How would we change this in order to allow evolution to paint regular patterns of weights across the synapses that make up this neural network, but it can paint different weights onto synapses that share the same three-dimensional midpoint? There's different ways we can do this. Anybody see one way to do this? Yep.
You could take the neurons from all the layers and just put them in a line, and those are three axes, and then you get non-overlapping weights.
Great idea. So we could alter the embedding. We could alter the way that we embed the neurons in three-dimensional space. And there is a 3D embedding in which no two synapses would overlap. Great idea. If we do that, then we can go back to having just our three inputs. That's not the way that the investigators did it. It's perfectly fine. How else might you do it?
You could have 6 inputs, 3 for the start-in neuron and 3 for the end-in neuron.
Which is exactly what the investigators did. So they had six input neurons. They had 6 input neurons, which corresponded to the x, y, and z coordinates of the presynaptic neuron. Remember, if we visit a synapse, the neuron at its base is the presynaptic neuron. That has a 3D coordinate. We take the 3D coordinate of that synapse's postsynaptic neuron, and that gives us a unique address in 6-dimensional space. Oh, there we go. Okay. That's exactly what they did. So it's a little bit, there's a lot going on here. We have HyperNeat, which is evolving populations of CPPNs. It's adding and removing neurons to those CPPNs using NEAT. Each CPPN paints a pattern inside a 6-dimensional hypercube. Those patterns end up being weights assigned to synapses inside a network that is embedded inside 3-dimensional space. This is quite a setup for this experiment. But hopefully, given our discussion, you can see there's a rationale for each of these design choices. So far, so good? Okay, now that they have this in hand, they're hoping that it, quote unquote, works, meaning that this setup makes it easier for evolution to evolve good gaits, fast-moving gaits, for this quadruped. From the robotics point of view, this looks like exactly like what we've seen before. The fitness function simply maximizes forward travel over a fixed period of time in a simulated world. How do they know whether this actually worked? They created a control, meaning they created another algorithm which is as close to the one that they're testing, which they're just going to refer to as HyperNeat here. It's as close to HyperNeat as possible, but in this control algorithm, they're going to switch off the parts of the algorithm that they're hoping is actually going to help evolution, right? And if they do, and the actual experiment evolves faster moving robots than the control experiment, that's proof that whatever piece of the algorithm they turned off in the control was helpful. Everybody see that? Okay, so this is kind of the black art of science. If you're trying to test a hypothesis, coming up with a good control is very challenging. A good control is something that is as close to what you're actually testing as possible, where the only difference is you're trying to turn off as little as possible. You're trying to make as little a change between the experiment and the control to really isolate whether that piece that's been turned off proved helpful or is supporting of your hypothesis. Okay, so in this case, they came up with the following control, which they're going to nickname here FT-neat, which stands for Fixed Topology Neat. So in this case, they're going to use the same neural network as in HyperNeat. They're going to allow for mutation and crossover, but not the addition and removal of neurons and synapses. So they're going to directly evolve the weights of this network. So in FT-neat, there's no hyper, there's no HyperNeat, there's no Cppns. You can count it up if we assume there's a synapse from every sensor neuron to every hidden neuron, and a synapse from every hidden neuron to each of the 12 motor neurons. However many synapses there is, that's what they're evolving using neat. But because there's a fixed number of synapses, they don't allow neat to add and remove synapses or add and remove neurons. Everybody see that? So FT-neat is evolving the synaptic weights of the neural controller directly. HyperNeat is evolving Cppns that paint weights onto the neural network that controls the robot. If HyperNeat is useful, if this biasing of evolution towards regular patterns of weights across this neural network, then HyperNeat should evolve faster moving robots than FT-neat. We wouldn't be spending an hour talking about this experiment if that wasn't the result. Okay, here we go. So first, the control. There's a whole bunch of these videos. You can go have a look at them on YouTube. I'm going to show you just two. They did multiple runs, multiple independent evolutionary trials of FT-neat. They did multiple independent trials of HyperNeat. At the end of all the runs of FT-neat, they took the one that did the best, the one with the highest fitness across all the evolutionary runs with FT-neat, and this is what it causes the robot to do. How regular is this gait? It's actually pretty regular. It's not a recognizable quadrupedal gait. It's also not perfectly regular. You'll see it's starting to sort of lose the plot here a little bit. Okay. That was the best they could do. That was the best they could do with the control. I'm now going to show you a second video taken from HyperNeat. Remember, they did multiple independent trials with HyperNeat as well. Among all the, I don't know how many runs they did. Let's assume they did N runs. They took the N champions, the most fit neural network from each of those N runs, and they played back the worst of those N champions. So the worst of the best. Here we go. Of all the N champions, this was the slowest moving. How regular is the gait? Really regular, right? Okay. This is a recognizable gait. Anybody remember? I mentioned it in passing when we were discussing legged locomotion. This is the Looney Tunes cartoon Pepe Le Pew gait. This is pronking, all four legs together. As I mentioned, there's several more videos you can go watch on YouTube. This is the worst of the best. You can go watch the best of the best. They were all much, much faster. They were all much, much faster than FT-neat. The experiment blew the control out of the water. So overwhelming evidence in favor of their hypothesis that regular distributions of weights across the neural controller for a robot tends to bias evolution towards regular gaits, which makes it easier for evolution to find fast-moving gaits, which we already know from our discussion of locomotion. Yes?
Is the trade-off that hyperneat requires a lot more computational power?
Good question. Does it? Does it require more computational power? And does it matter in this experiment? Think about your own code base at the moment. When you run the hill climber or the parallel hill climber, how many seconds of time does your code spend waiting for the simulation to end? Even with the graphics turned off. How many seconds does your code take to copy, mutate, delete vectors in your hill climber or your hill climber? It's vanishingly small, right? So, it's a great question. Of course, hyperneat is more computationally expensive. It takes a little bit more time to get one network to paint weights onto another network before you go. But it is vanishingly small compared to this part of the code, right? Okay. So one of the nice things about evolutionary robotics and most of AI is 99.99% of the time is spent in evaluating something, the robot, the neural network. The amount of time it takes to actually modify that network or modify that robot doesn't matter whether it's computationally expensive, whether it's done inefficiently. When you're implementing neurons and synapses, my apologies after the fact, the way you did it is probably the most computationally inefficient way you can propagate values from input neurons to output neurons. For your purposes, it doesn't matter. It doesn't slow down your code at all. The reason I put you through those steps is because I wanted you to actually have firsthand experience with wiring up and propagating values through a neural network. Of course, today we're in a high summer of AI. There's PyTorch. There's all sorts of machinery out there that you can use that will do all of that stuff for you. A lot of people working in the field of AI today have never actually wired up and written code to propagate values from the input to the output neuron. In my personal opinion, if you're going to go out and work in AI in the real world, you should know what's going on in the engine room of any AI system. That's what's going on in the engine room. Okay. All right, so back to this experiment. Hyperneat did way better. Given our discussion of biomechanics and locomotion, you already know why hyperneat did better, is because it tends to produce more regular gaits. Here are the results from two different Cppns for hyperneat. And what we're plotting here in each of these two panels is time steps inside the simulation. And each individual curve here corresponds to the hip forward and back joint angle. We've got four hip forward and backward angle. We've got four joints at the hip forward and backward. We're plotting the angle of those four hip joints. And here's the result from our Pepe Le Pew here, pronking. We can see that all of those four joints are moving in a perfectly regular pattern, almost perfect, not quite. And they're all in phase. They all have exactly the same angle. Here's a different gait. And if you look carefully, you'll notice there's four curves in here. Each of these four curves has more or less the same frequency. Each curve has more or less the same shape. So every leg is doing more or less the same thing. They're just doing it at slightly different phase offsets. So this could be cantering, trotting. It's not quite obvious from this picture. Still a pretty valid gait. Here are the two best evolved neural networks for FT-NEAT, and you can see obviously lack of regularity. Each of these hip joints has its own frequency, different phase offset. They have their own bias. Some are in the negative angles, some are in the positive angles. Things are literally all over the place in these two neural networks. Okay. We're going to now analyze a little bit more about why hyperneat is useful here. This is a plot we haven't seen before. This is a mutation plot. It's showing you for every mutation that occurred in these evolving populations, what was the result of that mutation? Let's have a look at the left-hand plot to start with. On the horizontal axis here, we have evolutionary time now, 1,000 generations. So imagine we have a population of Cppns that are evolving over time. We're going to focus just on mutation, not crossover. There's also crossover in hyperneat. Every dot here corresponds to a point in evolutionary time when hyperneat chose one parent to reproduce. That parent produced one child, and during that copying event, a mutation occurred. Remember, we're dealing with hyperneat. We have neat under the hood. So that mutation could be adding a neuron, removing a neuron, adding a synapse, removing a synapse, altering the weight of a synapse. So every point corresponds to one parent and one child neural network, where those two neural networks might be slightly different in form and probably slightly different in function. We're dealing with hyperneat, so those two networks are Cppns. I erased my Cppns here. We've got two different Cppns. We take each of those two Cppns and paint weights onto the neural controller for the robot, measure how far the robot moves, take the child Cppn, allow it to paint weights onto the neural controller, allow that neural controller to control the virtual robot, and record how far that robot moves. We now have two Cppns, and we have two corresponding fitness values, the speed of the robot. So far, so good? The height of each point represents the difference in fitness between the parent Cppn and the child Cppn. So far, so good? Okay. This is a semi-log plot. We're plotting the log on the horizontal, a log of 2. Okay. For our purposes, it doesn't really matter. We're just going to look at this overall pattern. Look at this point way up here. It's got a vertical height above 60. What this means is that the child moved 60 length units further than the parent. The child did way, way better than the parent. Let's pick another point way down here. This point has a value less than minus 60. This means the child Cppn caused the robot to move 60 length units less than the parent Cppn caused the robot to move. So far, so good? A value of 0 means what did the mutation do in that case? Absolutely. The mutation probably had no effect on the child. I think last week we talked about junk DNA. Inside a Cppn, there may be neurons and synapses that aren't even connected directly or indirectly to the output neuron. If you mutate junk DNA, it has no effect on the behavior of the network and therefore on the behavior of the parent. Yeah? Okay. If you look at this smear of blue for a moment, things actually don't look very good for hyperneat. It looks like there are huge numbers of mutations that cause the child to perform much, much worse than the parent. Yeah? Seems a little bit worrying. However, if we look at the control experiment over here, remember that in FT-neat, this stands for fixed topology neat. In this case, neat is evolving the synaptic weights of the neural controller directly. It's evolving the weights inside this network. No Cppns, no adding, removing neurons or synapses. If we imagine two versions of that neural controller, the parent neural controller and the child neural controller, they're going to have the same number of neurons and synapses. A mutation can only alter one or a few synapses. What's the overall effect of mutations in FT-neat compared to hyperneat? There's several differences. What's kind of the most obvious one?
great of an effect.
They didn't have as great of an effect. A mutation that hits the neural controller in FT-NEAT has less of an impact on the child's behavior. There's less of a difference in fitness between the parent and the child. Over here, the vertical spread is much wider. A mutation that hits a CPPN that paints weights onto a neural controller has a much larger phenotypic effect. And generally, that larger phenotypic effect is bad, right? If you open up your computer and hit it with a hammer, you make a big change to the insides of your laptop, probably not going to do very good things, right? Generally speaking, in evolutionary algorithms and AI in general, we're trying to create variation operators, things that alter a neural network by a very small amount, right? If you open up your laptop and if you really, 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 really know what you're doing and you go in with very, very, very fine tools, you might be able, even if you're operating at random, to make things a little bit better. At least the probability of doing that is a lot better than going in with a hammer. Yeah? Okay. Everything seems to hold up to our intuition except up here. HyperNEAT, the mutations in HyperNEAT are like a hammer. They're making big changes to the set of synaptic weights inside the neural controller. And quite a bit of the time, those changes are actually very large and for the better. How is that possible? This part differs markedly from this part, and it's this part that allows HyperNEAT to do better than FT-NEAT. How is this possible? What is it about HyperNEAT that allows a mutation to HyperNEAT to be both large, it has a big impact on the child, and positive? It makes the child behave much better than the parent. How is that possible? Any ideas?
The best thing I can think of is, like, as an example, if you tweak the cycle of the legs so that they're more in tune with one another, it would make a really big impact, possibly.
Okay, so you can imagine a mutation that's tuning the synchrony of the legs, that they move slightly more together.
Right, that would be a small mutation.
That's a small mutation.
On the CPPN, but
Yep.
it would make a big mutation or a big difference in the actual performance.
Absolutely, that's right. So you can imagine maybe altering or evolution mutating the weights emanating from the central pattern generator, tuning up the weights. But that doesn't really address the magnitude. You're right, tuning the synchrony is going to have an effect. Why do mutations in HyperNEAT tend to have high magnitude?
This is maybe just kind of a guess, but like
Sure.
because it's symmetric, is it making more changes like when it's doing the regularization than the FT version?
Absolutely, right? So when we were doing a few CPPNs at the board, I made one change. Well, actually, I made two changes. I erased the synapse coming from X and added a synapse coming from Y, and it made a huge change to the picture. We went from a horizontal gradient to a vertical gradient. So a mutation in HyperNEAT, by definition, has a big impact on the phenotype, regardless of whether the phenotype is a picture or a set of synaptic weights. Why do they tend to also be positive? We now have a good idea of why they have high magnitude. Why are some of them also very positive? HyperNEAT is going in with a sledgehammer. It's making a big change, and against that the intuition of that metaphor, a lot of those hits with the sledgehammer make things much, much better. How? How is that possible? Let's go back to the Pronking gate. Here's one of the gates produced by HyperNEAT. Imagine a mutation comes in and makes a change to lots of synapses that affect all the legs. But remember that mutations in HyperNEAT tend to restrict themselves to regular motion. So that big change is unlikely to cause one of the legs to start moving in antiphase to the others. It might, for example, speed up all four legs or slow down all four legs. That's definitely going to produce high magnitude and deleterious mutations, if it slows down, and high magnitude and big positive changes. If you tune up the frequency of pronking, you get something that suddenly moves a lot faster than the parent. We're out of time for today. We will leave things here. You have a quiz due tonight. You're starting in on the final programming assignment. See you Thursday morning. Have a good day.